Okay, this question is about rates of reaction. This phosphonate ion reacts with hydroxide ions, producing hydrogen gas as shown. A student completes an experiment to determine the initial rate of this reaction. The students used a solution containing phosphonate ions and measured the volume of hydrogen gas collected every 20 seconds at a constant temperature. The following graph shows the students' results. Use the graph in figure 1 to determine the initial rate of reaction for this experiment. Right, I've pre-drawn this on just because using the ruler is a little tricky, but you need to draw a tangent starting at 0, 0. That will get you one of the marks. So tangent starting at 0, 0. And then the calculation, so we've got the change in y here, which is 200, the change in x here, which is 38. So at this point here, I can now determine the gradient, and the gradient is the rate, because the rate is the change in the concentration, which is proportional to the volume of gas that is given off, divided by the change in time. So the gradient here is 200 divided by 38. So 200 divided by 38, which gives an answer of 5.26. And then the units here, so because we've got volume on the top in centimetres cubed, and we change that to a V. So what we've got here is centimetres cubed per second, which is that bit there. Okay, so this answer here, anything between 5 and 7 is allowed, and then so there's 1 mark for that, and then 1 mark for the correct units written like that. Okay. Part B, another student reacted different initial concentrations with an excess of hydroxide ions. The student measured the time taken to collect 15 centimetres cubed. Each experiment was carried out at the same temperature. State the relationship between the initial concentration of phosphonate and time. Okay, so there's a couple of ways that you can do this. So what we've got is time here, which is kind of not easy to look at. So you could convert all of these, or whichever ones that you're looking for, into 1 over t. So I'll do that, and I'll do it both ways. So 1 divided by 64 is 0.0156, 0.0156. And I'm only going to use these two here because it's doubled from 0.25 to 5. So I'll do 1 divided by 16, which is 0.0625. So this has doubled here, so that is 2 to the x equals, and then 0.0625 divided by 0.0156 is 4. Therefore, x equals 2. So the order is second order. The other way that you could do it is you could actually look at the times, and you could say, well, the concentration has doubled, the time has gone down by an eighth, which means the rate has gone up by gone down by a quarter, which means obviously the rate has gone up by 4, if you wanted to argue it that way. But sometimes it's just easier to look at these. So what we need to do here is state the relationship between the initial concentration and time. So concentration of the H2PO2 minus squared. Now that's proportional to the rate, but it's asking you to do the relationship with time, and rate is proportional to 1 over time. So if I just rub that bit out there, and there's the relationship there. Okay. Complete the diagram in figure 2 to show how hydrogen gas can be collected and measured in the experiments in part A and B. Okay, so 1 mark for this. You've got 2 options, so and it has to be properly sealed. So one would be to use a gas syringe, which will look a little bit like this. And then the alternative that you could do, if this was the pipe coming off, is you could do the stuff that you probably used to do at GCSE, where you collected it in an upturned measuring cylinder, a flask of water like this. And again, you've got to make sure that everything is sealed, that there are no gaps, that it's a proper cross-section. So 1 mark for either of those diagrams that are drawn there. Okay, D. Deduce the overall effect on the rate of reaction when the concentrations of both L and M are halved. So it's a half times a half squared. So a half squared is a quarter, and half of a quarter is 1/8. 1/8. So that means then that the order has gone down by a factor of 8 or multiplied by a half. Part E, the rate of the reaction when the concentration is L. The concentration of L is 0.0155. Calculate the concentration of M if the rate constant is that. So let's rearrange the equation first. So all I need to do now is put the numbers in. So 0.025 divided by 21.3 times 0.0155. So, and then I need to do the square root of that to get rid of that. And that gives me 0.275. Okay, so there's 1 mark for rearranging the equation, 1 mark for putting the numbers in and doing the square root. Okay, next part. Determine the overall order for the reaction. So the order, remember, is the sum of the orders that we have here. So define the term. Okay, well that's easy enough. So it is the sum of the powers or the indices to which the concentrations in the rate equation.